All right, let's start to talk about polymers. So, first thing I want to do, these are what the general public would call plastics. What I'd like to do is start by looking at the mechanical behavior of polymers. And they have a curve that looks similar to what we've seen for a metal. It comes up to a peak. Actually, that peak is where necking begins, but then there's something different. It may continue to extend out like this and support load well beyond the top of the curve there. So at the top of the curve, we have, just like we do for metals, we have necking. But then there's something interesting here that happens, right? We can get continued loading, continued load bearing. Continued load bearing, right? That was different from what happened for a metal. This is significantly different. A metal, when it necked, get that narrowing of the cross-sectional area, it's going to break there each and every time. For a polymer now, we somehow are able to get a neck forming, and then the neck doesn't break. What's happening? It gets longer. It continues to plastically deform. We've got to understand that. Before we do that, I'd like to define a few terms. So the peak of the curve here, because for a polymer, we get so much strain to failure, there's so much deformation that happens, it's actually pretty safe and conservative for us to just define this point here as the yield strength. So that's what we do. There's no need to mess around with a 0.2% offset yield strength or anything like that. So we just pick the top of the curve and call it the yield strength. And then there's a slightly different definition for where it fractures here, and the place where it fractures is actually just called the tensile strength. Okay, it doesn't have to be the same height or less than the yield strength. It often is, but that's not really of particular importance right now, exactly where the yield strength and tensile strength are relative to one another. The shape of the curve is what we want to look at, and to understand that, what we need to do is dive down into the microstructure of a polymer. And so here is a highly detailed look at the microstructure of a polymer. You can imagine this as a plate of noodles, a bowl of noodles, whatever you pick, spaghetti, udon, ramen, pho, vermicelli, whatever you like. I like to be culturally sensitive, so whatever kind of noodles you like, there they are, you pick them. And when we think about mechanical behavior of a polymer, we can think about these noodles or chains moving past one another. I want to further give you some details on the microstructure. So if that was where these lines, I'm just drawing lines, at the atomic level, the molecule may be made up of, as is often the case for polymers, carbons, strong bonds between them. We're going to elaborate on the type of bond there. It's a covalent bond, but we're going to cover that in detail later. And that's what makes up this chain, okay? Another thing I can look at is, well, how are we going to, well, this is, for example, specifically polyethylene. Sometimes we just call it PE. So how are we going to describe this? Well, the first way that we can describe this is we can say, well, what's the building block? Just like we did for a metal and a ceramic, we had the little unit cell. What's a convenient unit to use to describe a polymer? And that is what we call the Mur unit. And so we get some little bit of repeating chemistry like that. And what we do is we'll indicate like this with an N, meaning that this 2-carbon unit is what repeats. You may wonder where the naming comes from, because you might think, well, why didn't we call this polymethylene with 1 carbon? Okay, meth, eth, prop, bute, pent, hex. Those are the number of carbons in a unit. So polyethylene seems to be a repeating unit with 2 carbons, and in fact it is. But you might wonder, well, why don't we just call it polymethylene, or polymethane or something like that, because it seems to be 1 carbon. That's the smallest repeating unit. And I'll tell you this, that the naming is according to what we started with, the starting molecule. And in the case of polyethylene, we start with this molecule here, C double bond C with 4 H's altogether, 4 hydrogens. And that molecule there is technically called ethene, but commonly called ethylene. Okay? If you want to call this molecule polyethylene, you'd be correct. And in fact, in Great Britain, that's what they call it. In fact, I think they pronounce it polythene. In North America, polyethylene is the common way to refer to this polymer. And this 2-carbon unit is what we break that little double bond, and we get this to react, and one unit extends on to the end of the next, and you get these great, great, great long molecules. And that's, in fact, where the name polymer comes from, because this is the mer unit, all right? And the name polymer that I've been using here to describe what the general public would probably call plastic is numerous, right, polymer units. So we repeat these mer units many times and we get a polymer. So what I'd like to do now is explain here how we can get this continued load bearing, and we can explain that using this little model here of the molecules as noodles, or sometimes people refer to them as chains. In fact, often chains are used, I think, because there's links in a chain and they repeat, right? So, or strings, I suppose, you could think of as well, all right? So we want to do that. Now let me give you an actual example that you might have done before. So here's a plastic bag. You go shopping, you buy a lot of healthy food, as you do, and you find that the bag, the handle in particular, might stretch and it starts to become uncomfortable. It cuts into your hand. What's happening? What's happening? Well, you've started to plastically deform it, and perhaps it's even started to neck. And so that's what I want to do. With any luck, I can get this to actually happen here on camera. I'm going to stretch this bag carefully, and I'm going to get it to neck. So I'm going to stretch it here as carefully as I can. And between my hands, we should start to see it neck. Now the necking is going to be it's going to be subtle at first. If I take my hands off, you might just be able to see that in the middle there, so we take a look right here, it's changed color a little bit. It's kind of transparent or translucent where I have not deformed it, but it's beginning to become opaque where I deformed it. That's really interesting. Is there something happening to the microstructure that's causing that? Well, in fact, there is. You know, my glasses are made from a polymer that I can see through. It's transparent. We're going to elaborate on that later. I'm going to continue to stretch this out here, and what will happen is it will become very strong in this direction that I'm stretching it. It's quite strong. Oh, okay, and it ripped. But all the same, it's still stretched. Now, what happened here, this region here is necked, and it stretched quite a bit, and it got kind of a white color to it almost. And that's because, I'll show you, that is because what happens is, as we deform this, and it necks, and I'll give myself a little bit more space here, the polymer molecules now, and I'm exaggerating somewhat, but they become oriented with the loading axis. Or another term that's used here technically for this is sometimes it's called conditioned. Okay, so it's oriented with the loading axis, and so now what we're doing is we're stretching along the length, or with this plastic bag here, in this direction. I'm stretching those strong bonds, okay? I'm stretching the strong bonds, and then rather than these little weaker, so sometimes what I do is I indicate with these just little red dashes, the sort of frictional type forces that we get between molecules, okay? So these little things here are, at this point, I'm going to call them weak, but I also weak bonds, okay? But what I also want to do, because I appreciate that some of you may actually know this term, using the blue color, I'm going to give you the technical term. These are secondary bonds, okay? But that's in parentheses. If you don't know that yet, that's okay. We're going to get to that a little bit later. Van der Waals interactions, dipole interactions, that's what we're talking about with those things. At this point, though, because we haven't formally covered it, I'm going to call them weak bonds. So now we've got the strong bonds, these are the black lines here, oriented up and down with the loading axis, and it becomes stronger, and that's why it doesn't break. Back up here at the top when I showed you the stress strain curve, because we get chain orientation in here, and it gets stronger and the neck doesn't break, and it continues to load bear. But here's one last thing. Let's see if we can use this model to predict a behavior, because a model is only good if it can predict something for us. So what would happen then if I took this conditioned polymer like this with the molecules oriented, and say I loaded it this way? What do you think might happen? Well, you appreciate we're going to be just overcoming these weak forces between the bonds. So it should be pretty easy for us to stretch this polymer that way. And I'll show you if with any luck this will work. If I now take this polymer and I'm going to stretch it perpendicular to the way I was loading it originally, and you'll see it just deforms extremely easily. You might remember how hard it was for me to stretch it initially. But now this way I'm generally just overcoming those weak bonds, and I can stretch it one more time like this, line them back up again, I can stretch it this way, and it just comes apart so easily. Stretch it, line those molecules back up again. And that's the mechanism that we have going on in this polymer when it deforms, and that is why we can get this continued load bearing, which is so fascinating and which is unique to polymers. We don't have that in a metal. All right, thanks a lot.